So welcome back to this next SWAYAM session. So in today's session we will do a recap of what was done as far as the pedagogy content is concerned in the last class, and then we will come back to the question that we left off with as far as glass transition temperature is concerned in the context of polymers. But we also discussed that in fact glass transition temperature as a concept is not necessarily related only to polymers or restricted only to polymers. One could also think about glasses in the context of ceramics and also in the context of metallic systems. For instance, metallic glasses do exist. I am going to use the question that the student raised about the allowable gap between TG and TM to introduce something called the Kauzmann paradox. I mean, I wouldn't consider this to be a very fundamental concept that needs to be covered, let us say, at a first year material science course level, but since there was a curiosity driven question, I wanted to sort of bring that to this class. So we will take a look at this Kauzmann paradox, which essentially provides a limit to the TG. It provides a lower limit, in fact, it turns out, as far as TG is concerned. Okay, and then we will continue looking at some formal definitions, MER being a definition, and then we will look at some stereochemical definitions, tacticity and cis-trans isomerism. I believe your students would have studied something about cis-trans isomerism in their high school. Nowadays in high school organic chemistry syllabus, there is some coverage of cis-trans isomerism, but still it is helpful for you to talk about cis-trans isomerism to your students in the context of polymers. Tacticity is definitely a new word for a large number of students, and we will certainly look at 3 different types of tacticities in the context of polymers today. And finally, we will look at property determination as far as polymers are concerned. We won't do a large description of the techniques involved, but I will definitely walk students through it at a catalog level. If these are the properties you want to measure, these are the techniques that you could actually use. So that is sort of helpful for a first introduction level coverage of polymers, and especially if there are experiments to do with polymers that you are going to run in your laboratories, you can use that which I have given in order to sort of structure your property determination experiments. So here is where we left off, and before I come to that, I need to recap what we did as far as pedagogy is concerned. So in the last class we talked about something called the Piaget's theory of cognitive development. And we try to make an association with Bloom's taxonomy, and of course you have seen Bloom's taxonomy earlier in this course. So the Piaget's theory of cognitive development is primarily relevant for educators in general, but increasingly becoming relevant in school education, not even college education, school education. But I personally think it is very valuable even for college and university education. I will tell you why this is considered to be so important for school education, because it provided a platform by which we understood how children learn. So for instance, very young children, they would be very sensory motor in the way in which they learn. For them, senses are very important. They are very sensorial, and they are very movement driven, and as a consequence that is sort of the most basic way of learning. It turns out that adults do not necessarily outgrow that. There are adult learners who might also need a lot of sensory inputs, and this is something that we are beginning to learn through educational research in rather recent times, because Piaget, when he was doing his research mid 20th century, he sort of understood or thought that children essentially outgrow the sensory motor stage. Then there is something called as the pre-operator stage, then operator stage, construct operator stage, and a formal operator stage. And the operator there is the way in which a student is able to, or a child or a human being is able to work with facts and figures, create connects. And this is where it actually becomes important in the context of constructivism also. Constructivist theory of knowledge was discussed in this particular class. We understood ontological maps, for instance, knowledge maps, concept maps, mind maps, and so on. And in all of those things, what was very obvious to us was the human mind understands in terms of connects, in terms of coming with a schema, new information comes in and that new information gets integrated. The language that we used in not the last session but last session was it gets assimilated and accommodated. It's assimilated so that that is additional information that the student can use or the learner can use, and then it becomes accommodated in the sense that that is additional information that they can use for decision making, for problem solving, and so on and so on. You understand? So, the Piaget's theory of cognitive development was discussed in the last class, wherein we understood that the most basic level of learning is sensory motor. At some level, I think that there is a very interesting correlation with situated cognition that engineering researchers have been talking about, engineering educators have been talking about, wherein in engineering, doing is equal to knowing. If you can write a code, for instance, that is equivalent to knowing the programming language, it goes hand in hand. So, you don't separate out the doing and the learning, you don't separate out the doing and knowing part. So, the Piaget's theory of cognitive development looks at sensory motor aspect, which is a very basic aspect, and then the pre-operator aspect, wherein children don't think in terms of transforming knowledge, but they are basically absorbing information at a very basic level, maybe just by learning words, for instance. Alright, then they learn to construct, they learn to sort of use words in new contexts, and so on and so on. And finally, they use words, string it together, put it together in the form of sentences to communicate an entirely new idea, concept, maybe a story of their own. And that is when they basically learn a great deal. And my observation has been that, and this is also consistent with modern research on even college students also go through those stages. That is why I said that at some level what Piaget has taught us about the process of learning is consistent with what Bloom's taxonomy recommends or prescribes as far as the learning process is actually concerned. Okay, so that is really what we discussed in the last class. Now we'll come back to polymers, and one of the things that I left the class with and was the following, that is, let's describe this graph as thoroughly as possible, as carefully as possible. So you can identify 3 features of this curve which you want to communicate to me. Each of the group should discuss among one another and come up with at least 3 features of this curve. You understood? So you can describe that there is a straight line here, it follows y is equals to mx plus c or something like that. Here also is y is equals to mx plus c, where m is different, something like that. So you come up with a description, a 3-point description. Okay, so you discuss with one another and come up with a 3-point description of this entire curve, of this data that is actually projected, and let us see what information you are gathering from that. So that is one. The second thing is, what about the limits of TIJU? Okay, can I basically infinitesimally bring it close to this? Can I take it infinitely far from this? Okay, are there any limits at all? Are the questions that we will actually. So please discuss the first question. So the second question is a little deeper and harder to answer. So and that I will use it as an opportunity to introduce you to a slightly interesting concept, a concept I think is very interesting, called the Kauzmann paradox. But for timing, just come up with a 3-point description of this curve. Okay, you understand the question? 3-point description of the curve. Bullet 1, bullet 2, bullet 3. Yes, what are your observations? So you have completed 2 bullet points as of now. Okay.
C consists of 3 straight lines.
C 1, 2, 3. Yeah, very good. And this is near straight, no? This is near straight. Reasonable, yeah. So it consists of 3 near straight lines, C, and of course at this particular point there is a discontinuity. You notice that, right? Because if I take the limit at this particular point, it's not the same. So there is a discontinuity, right? So if there is a discontinuity, there is no derivative also, well defined. And there is a specific volume, of course. But here you see there is no discontinuity at all, right? And another thing is the glass transient temperature is defined based on an extrapolation. You extrapolate the curve here, extrapolate the linear portion of the curve here, and you would actually get TG. So the extrapolations are very funny because there is always a wee bit of subjectivity associated with it. So those of you who have done some kind of graphing would always know. I hope you get the point. That is, it's when you extrapolate this linear part and this linear part that you actually get the TG. And let's look at some more aspects. Now there is a shrinkage. Now this shrinkage is due to freezing. What does this actually mean?
Until all liquid comes to solid, the volume.
Correct. So that's equivalent to saying that the specific volume of a solid is larger or smaller than the liquid? Smaller, much smaller, because the atoms or molecules are more tightly sitting close to one another and so on, right. So, there is this shrinkage. So, it is because of a liquid to solid transition, isn't it? So, this is actually the solid to liquid phase transition, but there is no equivalent dramatic event that is actually happening. And then there is a phrase supercooled liquid. What does supercooled liquid mean? Can you discuss with one another? Why do you call this supercooled liquid? Can you discuss with one another just a wee bit for, let us say, a minute or two? So, why is it called supercooled liquid? Correct. So, if I were to do this, see, if I were to do this infinitesimally slowly, that means I take the liquid, I am going to lower the temperature of the liquid, and I am going to do it very slowly. That means it is a thermodynamic experiment, right. Then at this point, I would actually see a freezing event happening, and then I would actually come down. This one, on the other hand, I am not even giving time for the liquid to basically solidify. So, it is a liquid, though at this particular point it should have in principle undergone a transition if it was an experiment that was done slow enough. So, this is a supercooled liquid because it is a liquid below the dash point. Is it a liquid below the freezing point? Now, we will try to address this rather interesting question. I just got this article because it addresses the question that Smarak asked at some level about this gap between the glass transient temperature and the melt temperature. The figure is not very good, I am sorry for that, but I can explain this hopefully, or maybe I should get you to explain this, okay. So, this one is Sx minus Sl, where Sl stands for the entropy associated with the liquid. So, they are distinguishing between two phases. Sx is whatever that supercooled liquid phase is minus the liquid phase, okay. So, that is what they are actually saying. And what would happen? So, this one is the crystal. This X stands for the crystal. It does not stand for the supercooled liquid. This is the supercooled liquid, okay. This is the supercooled liquid. This is the entropy of supercooled liquid. Now, entropy associated with the crystal, entropy associated with the supercooled liquid. What do you think would be the sign of this? Sx minus Sl. Crystal minus the liquid. Negative. It has to be negative. Because the entropy, the crystal is a much more ordered state when compared to this liquid. Correct? That much makes sense, right? Now, notice what happens when you plot this difference as a function of temperature. When you plot this difference as a function of temperature, this is not a very good curve. Maybe I can show this in a slightly different manner. Yeah. And where do you see that? So, the entropy difference is crystal minus liquid. This is sort of Sx minus Sl. If this region just does not exist, it cannot exist. Why does not it exist? Yeah, can you just try that? That is right. You can actually do that. Yes, can you try that? No, that is fine. That is correct. Now, the one on top is actually liquid, right? So, you please label that L. Label this X in keeping with our this one. Yeah, fine. Now, this is S as a function of temperature. So, this is the typical shape of the curve. So, this is a qualitative argument as of now. Okay, this is a qualitative argument as of now. So, this is the shape. Now, S is decreasing as a function of temperature, isn't it? So, what would happen if I supercool it? I would actually have this continuing to go down, and at this particular point and beyond, the entropy associated with the liquid becomes less than the entropy associated with the solid. Did you see that? So, this is a solid. The solid entropy changes with respect to temperature like this. The liquid entropy changes with respect to temperature like this. If the liquid were to be supercooled, beyond this particular point, what would happen? The liquid would have an entropy that is lower than the entropy of the crystal. And since that is just not allowed, you would expect the system to freeze before it reaches this temperature. So, undercooling is allowed, but not infinitely allowed. So, there is a lower limit to which you can do this undercooling, and that is given by this point, and that is, so once you hit this temperature, you can expect a freezing event to happen. So, this temperature is called the Kauzmann temperature. So, it's called okay. So, if I have a liquid with potential for supercooling, it's true that you can supercool, but you can't do it infinitely. You are limited by the Kauzmann temperature. Very good argument, good. So, it actually, as a consequence, depends upon the specific heat capacities here and the specific heat capacities here, and how their integrals basically pan out over temperature. Now, this one has been taken from Wiki, and Wiki is something that has a CC license, Creative Commons license, just like NPTEL, and this can be used in this course. So, please note that you remember the extrapolation part. So, this is for the experimental data that the extrapolation is actually being done, and you can see that the measurement is dilatometric measurement. That is because you want specific volume as a function of temperature. So, you need to do dilatometric measurement so that you know how the volume is actually changing, the specific volume is changing, and so on and so on. And you will see that on the y-axis it is not very clear, it is delta L divided by L. And here is heat capacity as a function of temperature. Heat capacity is what? Cp. So, you are measuring Cp as a function of temperature, and they are determining glass transient temperature. How would that be made possible? Can you discuss with one another? I have the ability to measure Cv. I will also give you this portion to read amongst yourself, discuss among yourself. So, this is the Cv curve. So, Cp, sorry, and from this I have to determine the glass transition temperature. How would I do that? So, you are welcome to read this and explain to me how you would do this experiment. So, this is very interesting, you see. Different operational definitions of glass transient temperature are in use, and several of them are endorsed by accepted scientific standards. Nevertheless, all the definitions are arbitrary and all yield different numerical results. At best, values of TG for a given substance agree within a few kelvins of one another. One definition refers to viscosity, fixing TG at a value of 10 to the power of 13 poise. So, you basically look at the flowability, the viscosity of the polymer. When it reaches 10 to the power of 13 poise, that is the TG you say. As evidenced experimentally, this value is close to the annealing point of many glasses. So, this TG value is very close to the annealing point for many, and here the TG value is fixed as A. So, you have a certain Cp, you have another value, and then at a point where there is a sweeping change in the slope, you basically extrapolate, and that is the value. So, you do something very similar to the specific volume experiment. So, this is another independent way in which you can get the glass transient temperature, but the key here is, of course, that there is no one accepted IUPAC TG. Many of them are endorsed by the scientific practice, and at best all of them are within a few kelvins of one another. So, there is no point in giving glass transient temperature to third place after decimal in Kelvin, it is meaningless, you understand. And it is a depends on the cooling, it also depends upon the process by which you have made your polymer. And whenever you hit this value, you can define that as TG, or you can define TG based on the earlier graph, that is specific volume as a function of temperature, or by using Cp as a function of temperature. Wherever you see this change in slope is what you can actually use to determine your glass transition temperature. Either ways it will be the same trend, no? Because after all you are just normalizing it, it does not matter. But here it is Cp, and in practice if you multiply this particular thing by some constant, the trend still remains. It won't change this integral. It is just a scaling factor. In contrast to viscosity, the thermal expansion, heat capacity, shear modulus and many other properties show a relatively sudden change at the glass transition temperature. Any such step or kink can be used to define TG. This is interesting, you see. So, any such step or kink, that means it is essentially a change in derivative that they are actually looking for. And what they are saying is that the derivative changes tend to be much more dramatic when you are looking at this when compared to viscosity. So, there is a rheological way of defining glass transition temperature wherein you use a rheometer and say when does the viscosity become 10 to the power of 13 poise, but that is not as dramatic and as a consequence perhaps as easy to measure as, let us say, volumetric change, specific heat capacity change, even shear modulus change. This is interesting, you see. Why shear modulus change? Because the glass becomes flowable, it is rubbery by that point in time. So, these derivatives with respect to temperature are much more high, much more easily detectable when compared to this, and hence in practice people could use either Cp or shear modulus or specific heat capacity. And specific heat capacity can be readily measured by using DSC, differential scanning calorimetry, which is why this is actually helpful. Okay. So, and to be honest, you know, 10 to the power of 13 poise, the approach to it and the withdrawal from it will be very gradual. That is the whole point. When you, what do you mean by derivative? The rate of change, right. So, the rate of change would not be as dramatic as, let us say, a dilutometric change, and it has to do with measurement, that is all, nothing else.
How sudden is the change in heat capacity? Is it as sudden as the transition from conducting state to superconducting state, for example?
They are very different numbers, isn't it? Because there the change in heat capacity is very small, very small. The superconducting transitions tend to be.
No, I am talking about the conductivity all of a sudden becomes.
Conductive, that is very rapid, extremely rapid. It is a first order transition. Here that is not the case. You can see that it is a kinetic phenomenon. It is a much smoother transition. It is a more continuous transition. So, to come back and to summarize, maybe what we can do is just read this out. The glass liquid transition or the glass transition is a gradual reversible transition in amorphous materials from hard to relatively glassy state to a viscous or rubbery state. So, the viscous state is the rubbery state, and the viscosity coefficient that they consider for measuring TG is about 10 to the power of 13 poise. Okay. And an amorphous solid that exhibits glass transition is called glass. That actually answers your question. Are all amorphous solids called glasses? The answer is no. Amorphous solids that show glass transition are called glasses. Okay. And the reverse transition achieved by supercooling a viscous liquid into the glass state is called vitrification. So, you take a viscous liquid, send it into a glassy state. If you make a glass out of it, it is called vitrification. In fact, you know, vitrified tiles are sold. So, they are basically tiles the surface of which are actually made glassy. So, you take it to the liquid state and then quench it very rapidly so that it becomes very glassy, and that is basically the idea behind vitrified tiles, you know. So, they give rise to very smooth surfaces. In fact, glassy surfaces can be very smooth, and they can be sometimes atomically smooth. That is a very big advantage associated with glasses, alright. And glass transition temperature of a material characterizes the range of temperatures. This is interesting, you see. They call it a single temperature here, but it is actually a range of temperatures over which the glass transition occurs. That means there is no unique golden number based on the measurement technique you use. That is why I asked you, did they give qualifiers? If they are not given qualifiers, it is not a complete description of the data. You will have to give qualifiers. For instance, what measurement did you use? Okay, and how did you measure it? You know, did you extrapolate in a particular manner? If so, how? Did you measure the viscosity? Did you measure the specific heat capacity? Did you measure the shear modulus? Did you measure the specific volume? What is it that you measured in order to report the glass transition? This is, or did you measure the DSC, CP? Okay. So, these are the things that you need to measure explicitly or mention explicitly when you say that this is a glass transition associated with this polymer. Otherwise, it is not a complete description of the data. It is not a complete qualifier of the data. You understand? Now, hard plastics like polystyrene, PMMA, this is called polymethyl methacrylate. In fact, it is a very widely used commercial polymer, PMMA, polystyrene, have glass transition temperatures are used well below their glass transition temperatures, that is in their glassy state. The TG values are 100 degrees or above, while elastomers are used usually above their TG. So what does that tell you about elastomers? PMMA, is it likely to be hard or rubbery when you are using it? Hard. While if you look at all of these things, for instance, polyisoprene, polyisobutylene, it will be rubbery. So those would be things that are easily bendable, deformable, while PMMA, for instance, will not be easily deformable. Now in your pressure cooker, the handle is usually covered by a polymer. Do you think the glass transition temperature of that polymer is high or low? Lower than room temperature or much higher than room temperature? Much higher than room temperature. That is why it is hard, it is brittle. But the erasers that people use, the glass transition temperature associated with that, is it much higher than room temperature or much lower than room temperature? That is why it is highly deformable. So now you have an understanding. So if you see something that is hard, this one is a plastic. So do you expect this one to have a glass transition temperature much higher than room temperature or lower than room temperature? Much higher than room temperature. So this was a helpful concept, isn't it? And despite the change in physical properties of material through glass transition, the transition is not considered a phase transition. This is very important. Rather, it is a phenomena extending over a range of temperature defined by several conventions. And there is no one uniform accepted convention. That is another important thing. Such conventions include constant cooling rate. That means when you are cooling it, cool it at a constant rate. Okay, and you will have to define the cooling rate also. If you don't define the cooling rate, that is still not a complete definition of the glass transition temperature. So you will have to tell, number one, the physical property that you have used to define the glass transition temperature. Number two, as and when you are cooling it, at what rate did you cool? These two things need to be mentioned. And then and only then should you report the TG value. Otherwise, it is meaningless. That is why in that other data, you gave a number. So of course, the number is still meaningful because you can say, okay, whatever is the number that you do measurement on will be in that vicinity, plus or minus 10 Kelvin or so. But it's not complete because it should have mentioned the physical property that was measured, for instance, viscosity or shear modulus or specific heat capacity or specific volume. And last but not the least, very importantly, cooling rate. In the absence of it, you wouldn't be able to actually completely define TG. Alright. Alright. Upon cooling or heating through this glass transition temperature, the material also exhibits a smooth step in thermal expansion coefficient, and you have seen that step. Okay. And it is that step that is actually used for extrapolation and determination of TG. And we also, thanks to Varada, came up with an explanation for the Kauzmann paradox, and we came up with a lower limit below which you cannot have a supercooled liquid. It will always solidify. And that paradox is called the Kauzmann paradox. Paradox is called the Kauzmann. What is the paradox? The paradox that exists here. This is the paradoxical region. I extend this, I extend this, I extend this. This becomes a paradox. And because paradoxes cannot exist in nature, before this solidification should have occurred. So this is the Kauzmann paradox. This is the region of Kauzmann paradox. Now there are some more words written out there. Let's just write it out once again. Mer, stereochemistry. And you may or may not know the meanings of these words, that's alright. And this is tacticity. This is divided into three parts. Iso, syndio, A, tactic. This one is cis, trans, isomerism. So why don't you look at the definition of the word mer? What is mer? And there are things here. Let us say copolymer. What does copolymer mean? Block copolymer, graft polymer. So we'll learn about mer, and from that we'll try to learn about copolymer, block copolymer and graft polymer. So why don't you use your data and help me? So why don't you come and write it out here, whatever you know, maybe 2 or 3 keywords you can do, make a knowledge tree. Come here please. So for mer, what are the 1 or 2 items that you want to actually write? So you can make a branch there. Spend 2 minutes, you can discuss with one another also. You can show the definition and identify 2 or 3 things that you might want to write associated with mer. And 2 or 3 things you want to write associated with block copolymer, and then block copolymer, then graft polymer. Just 2 or 3 things. This is student work. You can discuss with one another whatever you are getting. Identify 3 points and show it to one another, write it out. So you can draw a picture if you want, if it is easier for you. If you want to just visualize and explain your visualization, that is also fine. So let us see, linear branched polymer. So you can draw the diagrammatic representation, schematic representation and show it to me. So can I have one of you come and start drawing? You can show one graphical representation and explain to the class, that's also fine. So Bodhi, do you want to try? Just one representation for each of these. Mer is a unit, just a unit, a chemical moiety. Okay.
So is it exactly same as monomer?
Need not be, no, because your monomer could be a combination of mers, in which case, so you have mer 1, mer 2 and that is basically repeated, then in which case this becomes the monomer. Can you just draw it and show it? So here A stands for mer, so you have mer 1, mer 2 and so your AB basically becomes the monomer.
So if X is the monomer, the polymer will always be XXXX.
Yes, yes.
If it is represented as AB,
yes, and then you can ask the question, what is that X made up of? If that X is made up of AB or let us say A, then it is actually a block. A, then it's a block that is actually repeating. Yeah.
Now it's same polymer. Now it can be branched. So for example, A, B, and again.
So maybe you can erase it. You can erase whatever is obfuscating the board, making it difficult for people to understand. So now what are you drawing? So mer is this. This is mer 1, mer 2, right? So let me just. So this is mer 1. This is mer 2. Okay, fine. And then this is the branch. No, so yeah. So if you did not have the branch, then you would have a linear polymer. So that is the distinction between linear and branched. So if there could be lot of branches, but you truncate all those branches, what is remaining is actually a linear polymer. So linear polymer and branched polymer. Very good. Next is block polymer, graft polymer. And what is copolymer? So if there are 2 mer units, like this is a copolymer actually. This is a copolymer because if it was just A, then A is the mer, A is the monomer and AN is the polymer.
So
but here, yeah. So when you have more than 1 mer, you have a copolymer. So it involves the union of 2 different kinds of mers. So that is what this polymer is. Now what is random copolymer?
So random means like we have A, B, then again B, like
yeah.
no particular A, B,
Yeah, correct. So I could basically have some AN, BM in any sequence and AB, O in any sequence, and in which case it basically becomes a random copolymer, right?
In this case, we cannot define monomer. Yeah, we cannot define a specific monomer.
Yeah, so but there is a copolymer, but here you have, you see. So, or you can just define it as A and
B are monomer.
No, their question is, see the distinction between mer and monomer, that is really the question. So, monomer is whatever is repeating in order to give rise to the polymer, that was the definition that we looked, the repeat unit, in other words is the monomer. Now, what happens if you have more than one mers? Okay, so then you can have repeat units like that, but you also have regions wherein there is random mers, there are random mers. It is still a copolymer, no question about it, because it still has more than one mer, which is a fundamental definition of the copolymer, you see. It has still more than one mers. Did you see that?
Yeah.
So, in which case it is still a copolymer, and it is a random copolymer. It is a random copolymer. And when would you expect it to be a random copolymer? So, I will give you some constraints. For instance, AB, they have very high binding energy. AA has very low binding energy. BB has very low binding energy. Then what will be the population of each one of them? Which one will have the highest population? AB will be having the highest population, right? Because this is a more stable unit than this or this. So, this will have higher population. So, if you look at the enthalpies associated with these mer and mer interaction, if you can look at the enthalpies of interaction between them, that gives you a fairly good idea as to the populations that would exist in these random copolymers. It makes a lot of sense, isn't it? Very good. So, when there are two mer units, the polymerized system is called as a copolymer. Now, that copolymer could be a random copolymer wherein you have these two mers randomly positioned anywhere. So, you have some AM, BN, ABM along the structure of the copolymer. If one block of a mer is followed by another block of a mer, so by this definition, can you just draw what a block copolymer will look like? Yeah, so correct. So, you have AB, 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 or I could have AN, BM, AN, BM, AN, BM, AN, BM, then also it would be a block copolymer, isn't it? So, I have a block of A, block of B, block of A, block of B. So, I have a block copolymer. Then when the mer units alternate after each other, they are called alternating copolymer, AB, 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 alternating copolymer. And in that case, what do you think about the enthalpy of AB interaction when compared to AA and BB? Yes, AB, the binding energy is higher. And when a certain side chain comprising of a certain mer combines with another growing side chain made up of a different mer. Now, this is interesting, you see, it has a side chain comprising of a certain mer, alright, a certain side chain combines with another growing side chain made up of another different mer. It is called as a graft polymer. So, you have one thing growing, another thing growing, and then they basically link up. So, it is grafting.
Here like, so not A, so here you see is coming.
Yeah. Yeah. Now, what would determine this? Ultimately, it is chemistry, the reactivities of this species, the functional group here and the functional group here, that determines whether or not grafting would happen, branching would happen, purely linear stuff would happen, and so on, isn't it? Okay, by the way, do these structures, these underlying structures determine whether or not this polymer can be crystallized? I will do slow cooling of this particular polymer. Okay, I could do slow cooling, I could dissolve it in a solvent, do slow and vaporize the solvent very slowly, or I could do melt cooling, I could melt it and then cool it very slowly, or I could do some crystal growth techniques. For instance, put a seed of the polymer of a crystal inside the polymer and slowly pull it out. I could do all these techniques in order to grow a crystal of this particular polymer. But I am giving you two different situations. One is wherein you have a linear polymer, the other one wherein you have a grafted polymer. Where do you think is a better chance of getting crystallinity? Makes sense, right? Because this linear can actually go, it can actually form structures. It's a chain. So, I can actually use the chain to form structures, but the other one is a jungle. How do you actually fold it to give rise to orderly structure? And as a consequence, the presence of side chains, bulky side chains, etc., reduce the possibility of getting crystals. So, I knew somebody who spent 3.5 years of her PhD just trying to crystallize a protein. That only tells you how nasty that protein is, of course, but it also tells you how complex the side chains and bulky side chains were. So, when she got the crystallization, she was all up and down. She wanted to give a party and all that because it was so difficult to crystallize. Try that, compare that with the crystallization of something like sugar. You can do it in your kitchen overnight. You know, you have saturated solution of sugar, you put a piece of sugar and around that you will actually get crystals. While if it's a protein, if it's a polymer, it's so hard to crystallize. But crystallization plays a very important role because you can study the atomic position with respect to one another. In fact, this was important to studying the structure of DNA, isn't it? Without doing DNA crystallography, we wouldn't know that DNA was a helical structure. Today, when people make molecules, large molecules, small molecules, materials, they study the crystal structures, they do the XRD patterns, and from that they deduce what the crystal structures are, and from that they deduce what the atomic arrangements are with respect to one another, right? I mean, it's so fundamental an activity, and yet when it comes to polymers, getting crystallinity is a very difficult challenge. Very, very difficult challenge. Now, the degree of crystallinity, do you think it will inform things like the TG value? Will it affect the TG value, the glass transition temperature? Of course, it will affect the glass transition temperature, and it goes back to what I said in the last class, that is the atomic arrangement with respect to one another determines the glass transition temperature as well. Very good. Now that you have studied copolymer, block copolymer and graft polymers, let us look at tacticity and cis-trans isomerism. So, can you look at tacticity? There are three types of tacticities, iso, syndeo and atactic. So, can you just look at the definition of each one of them, please? And then again come up with cartoons here. So, you can look up and come up with cartoons. And by the way, before I forget, I just wanted to tell you this. So, this is from Callista, linear. So, it's a single chain, branch chain you can see, and then this is, in addition to grafted, there is something called network. So, wherein it's all coming together in the form of a three-dimensional network. Okay. So, network polymers. Oh, this is not from Callista, this is from Oxford Primer. Yeah. So, tacticity, were you able to find out? Cartoons for tacticity. Why don't you draw here? Cartoons for tacticity.
So, one side.
Yeah,
side.
correct. That's right. So that would be isotactic. What you showed is isotactic. So, if this R is put on the same side, it would be isotactic. If it is put in alternating sides, then it would be called syndeotactic. If it is randomly distributed, it would be called atactic. Alright. So, does tacticity influence the TG? Will it influence the degree of crystallinity or the ease with which? Of course, okay, no question about it. Now, if this R side chain that is there, if it is a very flexible side chain, it's a very flexible side chain, okay. Then is it likely to be, you can write down these two words, thermoplastic versus thermosetting. Thermoplastic versus thermosetting. So, which of these two possibilities are there? So, read the definition of thermoplastic and thermosetting, and now based on the definition of thermoplastic and thermosetting, think about what would happen if R was very flexible as opposed to rigid. Would it be thermoplastic or thermosetting? Thermoplastic. So, thermoplastic. So, what is the definition of thermoplastic and thermosetting? That is correct. So, if you have a flexible R group, then you are likely to have a thermo. So, can you look at the definition of thermoplastic and thermosetting, please? Can you just look at the definition, formal definition, and tell me the formal definition, please? They soften when heated.
Harden when it cooled.
And then?
The process is totally reversible. And
the process is reversible. So, if it is a flexible system, if it's a flexible side group, then it allows you to actually heat, make it soft, cool, make it hard, heat, cool, etc. But on the other hand, if it is not a very flexible side group, then you heat it, it might actually fix the network, and as a consequence, the reversibility could actually get lost. Okay. Now, look at this question. You are given two different polymeric materials, both having same molecular formula, similar monomers. How can they be different? We have discussed differences already. So, read this answer and explain to one another. Okay. So, you find out when you discuss, identify just two bullet points based on which two polymers can be different. So, write down. So, the answer is already given there. You can choose 2 bullet points or 3 bullet points and write it down and explain to one another, and I will ask you to explain it to me. You understand? So, the differences could be of very many kinds. For instance, the degree of crystallinity could be different, the final morphologies As seen under a microscope, they could be different, right? The glass transition temperature could be different, the strengths could be different, the thermomechanical properties could be different. If the crystallinity is different, the reactivities could be different, the stereochemistry could be different, the tacticity. And what is cis-trans isomerism? Can you look at cis-trans isomerism and explain that to me, please? Cis-trans isomerism and explain that to me, please. Can you read about cis-trans isomerism? You can use your data. So you can use your data, look at cis-trans, give me an example, go to the board and explain. So you could erase this part. So Naveen, do you want to give an example of cis-trans? Oh, before that, what are the two differences that you could actually see between two polymers? So this is the same composition as this. What differences can I actually anticipate between two samples prepared of the same polymer, same composition? What are some of the distinctions? Crystallinity, very good. TIJU, glass transition temperature, very good. Strength, mechanical properties, very good. Chemical reactivities could be different, very good. Yeah, and as a consequence, morphologies could be different, electrical properties could be different, absolutely. So polymers as a consequence are tremendously complex, as you can imagine. Okay. Now, if clearly you will have to measure these polymers, okay, you will need to do measurement, and these are the techniques that are used for measuring properties of polymers. If you wanted to measure glass transition temperature, the simplest and most widely used tool, I have not given the full spectrum of tool, and I have already told you that DG can be measured using multiple approaches, but the most widely used tool is differential scanning calorimetry. So it allows you to measure Cp, and then the change in the slope is where you actually use the extrapolation technique in order to determine the TG value. Molecular weight is actually a colligative property, and it can be determined using colligative and diffusive measurements. Alright, for example, you can measure osmotic pressure, or you can also use chromatographic techniques and determine the weight associated with the polymers. Okay. So chromatographic techniques and osmotic pressure. Alternatively, as I told you, you can do viscosity measurement, so that is the rheological property measurement. Next is molecular structure, most widely deduced by using NMR and X-ray scattering. And this, by the way, is very widely used as a technique in polymer chemistry, polymer science, organic chemistry and so on. NMR allows you to determine how atoms are positioned with respect to one another. And carbon based NMR is very widely used, isn't it? Proton NMR is very widely used for studying organic compounds. It says polymer crystallinity by using densitometry. The more dense it is, the more dash it is. Crystalline it is. Very good. Next is degree of crystallinity can also be determined by using small angle X-ray and neutron scattering. Other techniques can also be used in conjunction, such as wide angle X-ray scattering. So it is good for you to sort of know that this is the catalog of techniques that are used in order to study polymers. Now here is an interesting correlation. This is the melting as well as glass transition temperature that is plotted. This is Tm and this is Tg as a function of molecular weight, and note that this one is a logarithmic scale. Did you notice that? It's a logarithmic scale. 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3. So it's molecular weight. It's increasing in the logarithmic scale, and that means the degree of polymerization is increasing in the logarithmic scale here, and as a function of temperature. And this one is Tm, the melting point, and Tg, the glass transition temperature, increases, saturates. And remember, this is a logarithmic temperature. So can you come up with a functional fit for this? If you had to come up with a functional fit for this, what would that be? It's increasing and saturated. It's like an S-shaped curve, that you would have seen somewhere else. So it should be some constant plus the logarithm of temperature divided by another constant plus the logarithm of the temperature. Typically the numerator the constant can be set as 0, in which case it would increase and saturate. So this is a very interesting result, okay, wherein the molecular weight is related to these two measurables, things that can be measured rather easily by using calorimetry and so on. So with that we will stop. So what are the lessons learned today? Can we just discuss that? Of course, on the pedagogy side we revisited Piaget's cognitive development theory and learned that of course the students here would be capable of formal operator based thinking. By that what we know is they will be able to think in terms of abstract concepts, apply concepts to new settings and so on and so on. And then we sort of saw the consistency between that and the formalism of Bloom. And then we continued this polymer based discussion by starting off with where we left off last time. Last time we had left off when we discussed the difference between glass transition temperature and melting point, and finding out whether there can be a lower limit to the glass transition temperature. And today we actually came up with an argument saying that there is indeed a lower limit for the glass transition temperature, and that is given by the Kauzmann paradox based argument. So Varada very nicely came up with an argument for that, a graphical representation and corresponding qualitative argument associated with it. Then we continued looking at TIJU measurements and the fact that TIJU measurement, there is no one single accepted method. There are a wide range of methods wherein you use specific volume, specific capacity, density, or specific volume is the same essentially. Densitometry measurements would be specific volume measurements, viscosity being the other, so there is rheological measurements and so on to determine TG, and in all of the cases the TG would be plus or minus 10 Kelvin within one another. But what you learnt is that you cannot simply give TG as a single number, you will have to mention the method that you use in order to get the TG, number one, and also mention the dash rate, cooling rate. And then we also noticed that between two polymers having exactly the same composition, there can be some extraordinary differences, crystallinity being among them, TG being another, morphology being another, and also clearly thermophysical properties, electrical properties and so on could be fundamentally could be quite different. We looked at the distinction between mer, monomer, polymer. We understood what block or copolymers are, block copolymers are, graft copolymers are, branched, linear and network polymers are, right? Mer, monomer, polymer, linear, branched, network. And then we also looked at graft polymers and block copolymers, and we looked at random copolymers, right, random. Then we also looked at stereochemical aspects, for instance tacticity, iso, syndeo, atacticity. One type of geometrical isomerism that we did not discuss yet is cis-trans, so that is homework for you. So, but we did discuss tacticity, and we saw that tacticity does inform and influence things like the glass transition temperature and so on and so on. And then I asked you some interesting questions about what would happen if the side group was flexible. The answer is you could actually expect it to be thermoplastic as opposed to thermosetting. And over and above that, we looked at a spectrum of experimental techniques you could use to study various properties of polymers. For instance, if you had to study the molecular weight, you could study it by using colligative or diffusive properties. That is a transport property essentially. Makes sense because weight does influence the transport, and glass transition temperatures can be studied by using these techniques. Molecular structure very often studied by using NMR and X-ray scattering. Crystallinity degree is very often determined by using SAX, it is called small angle X-ray scattering or wide angle X-ray scattering. You can also study it by using neutron scattering. And polymer crystallinity is sometimes also determined by using densitometry. Makes a lot of sense, and higher the density, more crystalline is the sample. So with that we will conclude, the homework being cis-trans isomerism. Okay. So thank you very much for being with us. We will see you soon in the next YM session. Thank you.